Hey guys, this is video 9.9, energy calculations that are coming back to back with the specific heat note video from 9.8, kind of continuation. Now we're going to do the math behind the concepts that we learned in the last video. Now I will say this will probably be a little bit longer of a video because I'm going to work through several problems. So if you get it kind of early on and want to go through and work all the problems and skip ahead to check the answers, go ahead and do it. Otherwise, you can feel free to pause and kind of fast forward as needed because, like I said, I'm going to work these out, and so it's going to take a little bit longer just to let you know ahead of time. So jump to page 17, all right, 9.9, energy calculations. And all of these, really, guys, we're going to kind of break it up into two groups. So we have the first set, which is temperature changes, and the second set, which is on the next page, are dealing with phase changes. Okay, so we will talk about how these relate to heating and cooling curves a little bit later on, after I know everybody's through all this toward the end of the week, as we go back and redo our or fill in our foldable that we started making. So good news is these three formulas that we're going to use in this video are all found on table T, excuse me. Table T in your reference packet. These are the three formulas right here. This first part, we're going to talk about Q equals MC delta T. Okay, notice all of these variables are defined for you on table T as well. This is a screenshot from your reference table. I want you guys to flip to your reference table. If you don't have it out, make sure you have it out right now. Notice C for water, and then H, F, and HV that we're going to talk about. These three are all found in your reference table as well on table B. Okay, so you have a lot of this information. This is really just plug and chug. You've got to solve for an unknown variable and be able to identify that, and then just go from there. So compared to some of the conversions and stuff we've done, hopefully this is a little bit easier for us. So note that temperature, though, based on those values, if you look on table B, for our value of C, okay, again, which is the specific heat capacity of water, our unit is 4.18 joules per grams times Kelvin. So because of Kelvin being in our unit, we have to make sure that our temperature values, we convert those to Kelvin. Okay, so it's going to be a little bit extra work, but it's still not bad because you have that conversion factor that is on table T as well, between Celsius and Kelvin. Note that you can also arrange this in many different ways. This is one type of question you could be asked, is like, what's the specific heat capacity of a certain substance? And then you would solve for C, and then you'll be given Q, M, and delta T, or be able to figure out delta T. Delta, guys, again, just means change, so it's the change in temperature. Let's jump into some problems and kind of go from there. So, example 1, when a sample of 25 grams of water is cooled from 20 degrees Celsius to 10 degrees Celsius, how much energy is released in joules? First thing you should do, and you're going to see me do this with every single problem, is I'm going to write out what my variables are. I'm going to pull them out just like I've done all year long. So, Q is what I'm looking for. Okay, joules is Q, so that's what I'm looking for. M, I'm given my mass, 25 grams. Okay, C, notice it's water, so my specific heat value, I'm going to look on table B, 4.18 joules per gram times Kelvin. Now temperature, notice I have two temperatures. This is going to be T2, this is going to be T1. If I look at my Q equals MC delta T formula, because notice how this is a temperature change, okay, I'm using my Q equals MC delta T. So we're focused in the first part of this video on this formula. All right, we'll talk about the other two in the second part, and then when it comes to practice, they're all going to be mixed together. You're going to have to identify which one you have to use. So if you see a couple temperatures and it's talking about a temperature change, you're going to be using Q equals MC delta T. Now notice, guys, delta T is the change in temperature. How we calculate that is going to be final temperature minus the initial temperature. Okay? That's how you do a change in anything. So kind of T2 minus T1. So that's why I've labeled this as T1 and T2. So my delta T is going to be 10 degrees Celsius minus 20 degrees Celsius. When I do that, that's going to be a negative value. And that is okay, because what do you think a negative means in terms of temperature change? Are you gaining heat or are you losing heat? Well, if it's a negative change, meaning you've lost heat, that means you're releasing it, okay? So if you get a negative value here, that means you're releasing heat energy, okay? It's being released. So keep that in mind. So my delta T is then going to be negative 10. So now we have all the variables we need. We can solve for Q. So Q equals MC delta T. Okay, the more work you show me, the more credit I can give you if you mess something up. So I encourage all of my students to show as much work as I'm showing with units. Okay, 4.18 joules per gram times Kelvin. Now notice this is degrees Celsius. Okay, so we need to convert our temperatures. Now you could do it two ways. If you can recognize in your mind that, hey, I've got a temperature change taking place, we defined in the last video that for every 1 degree you change in Celsius, you're changing that many in Kelvin. If you can't remember that, what I encourage my students to do is to just convert these to Kelvin right away, and then you know you're right. So if we're going to convert this to Kelvin, I'm going to add 273 to it. So this is going to be 293 Kelvin, and this is going to be 283 Kelvin. Now, when I do the math and I do my subtraction, 283 minus 293 is going to be the same thing, negative 10 Kelvin. So if you can recognize that when I have a temperature change, okay, this is not going to hold true necessarily with other ones, but when I'm changing my temperature, the change in Celsius degrees and Kelvin degrees are the same. So this is going to be a negative 10 K for my temperature change, my delta T. Now it's just plug and chug at this point. Grams are going to cancel out. Kelvin's going to cancel out. We're left with joules, which is what we want for a Q value. When we do this math, you should get negative 1045 joules. Remember, sig figs don't necessarily matter unless they ask you for it. If we were going to convert this to correct sig figs, okay, we would want 3 because all of our original numbers, our mass number and temperature numbers, had 3 sig figs. So that would be 1, 2, 3, and I would round this up. So my correct sig fig rounded answer would be 1050 joules. Now, notice this is negative. So if you see a negative number, guys, that means that energy is released. Okay? If it's a positive value, J, it's going to be absorbed. And if it's a negative value, it's going to be released. So, pretty straightforward. Identifying your unknown, solving for the unknown, and then plugging it in. Okay, so if you feel confident, go ahead and work these out. You can skip ahead. Like I said, this video could be a little bit longer because I'm working the problems out. Now, so pause it, try these on your own, check your work, and then we'll talk about the phase piece or kind of continue working with me. So in this one, I'm going to move a little bit faster, okay? Specific heat is what I'm looking for now. If I look up here, specific heat, guys, is C. So C is what I'm looking for. I have my mass, which was given as 4 grams. My delta T, so heated from 0 degrees to 41 degrees. Well, if I want to do that math, this is T2, this is T1. Again, you can convert it to Kelvin if you want, or if you recognize, hey, 1 degree Celsius change is the same as 1 degree Kelvin. So 41 minus 0, so my delta T, guys, is going to be 41K because I changed 41 degrees. And then I'm also given Q, which is 32 joules. So now what I encourage you all to do, before you plug in any numbers, solve for your unknown variable. So Q equals MC delta T is our normal formula. Well, now I'm looking for C. So how do I get C by itself? I'm going to divide by M and I'm going to divide by delta T on both sides. Okay, M's are going to cancel out here, delta T's are going to cancel out. So now I have C equals Q over M delta T. So now I can just plug in. So 32 joules divided by 4.0 grams multiplied by 41. Now make sure that when you do your math here, guys, that you don't go too fast and forget it. We have to do this multiplication on the bottom first, then take 32 and divide by that. So when I do 32 divided by the bottom multiplied together, my final answer should be 0.195 joules per gram Kelvin. If I was going to put this in correct sig figs, 2 sig figs is what I would have, so this would round and be 0.20 joules per gram times Kelvin. Okay? So if you did that one with me, I encourage you right now to pause this video and try this you-try problem on your own. All right, so how much heat energy? So I'm looking for energy, that's going to be Q. 55 gram sample, mass is 55 grams. Temperature change, this one is not as easy to maybe do in your head, but again, just subtract your second temperature minus your first one. When you do that, it's going to be 94.6 minus 22.4, so you would get a value of 72.2 difference, and we can just say that's Kelvin because, again, 1 degree Celsius change is the same as 1 degree Kelvin. Now, specific heat, notice that this is aluminum. We have an aluminum sample. We can't use that value from table B. So notice, guys, if they switch up the substance, they have to give you the specific heat value because you don't have access to those and you're not going to memorize them. That's absurd. So we have 0.897 is what we're going to have. Now it's pretty straightforward. Q equals MC delta T. So 55 grams multiplied by 0.897 joules over grams Kelvin times our temperature change of 72.2 Kelvin. Kelvin cancels out, grams cancel out, so we're left with joules, which is a good unit. Now, if I'm thinking about sig figs here, guys, I'm looking at my least number of sig figs, my measurement, that's going to be this 55. So 2 sig figs is what I would round to if I had to round to correct sig figs. So if I just do it all out, you should get an answer that is 3,562 joules. So if I was going to round to sig figs, let's take a look at this. Here's my 2 sig figs. So I'm going to look at this number 6 to round up. So if I was rounding it to correct sig figs, it would be 3,600 joules. Okay, so these types of problems, these are temperature change problems. Well, what happens if you're not changing temperature and you're changing state of matter? That's where these two formulas come in. Again, these two formulas, guys, are also on that same spot, that same formula piece on table T. Okay, if you look back, right, now these next two we're going to focus on here. Q equals MHF and MHV. Notice, guys, Q can be, I just realized this, Q can be either capitalized or lowercase. You're going to see it the same way. Don't get confused. It means the same thing. Okay, some people will capitalize it, some will lowercase it. Don't stress about that. So now we have Q equals MHV and Q equals MHF. So remember, all of these are defined. All of these variables are defined for you on table T. HF and HV, heat of fusion, heat of vaporization. Okay, so this is table B right here. Fusion. You've got to know what these two terms mean. Okay, fusion relates to what two states of matter. If you can't figure out or remember fusion, guys, vaporization you should know. Vapor. So this is where I'm going from a liquid to a gas or vice versa, gas to a liquid. What's the difference between liquid to gas and gas to liquid? One's an absorption of heat, one's a release of heat. Gas to liquid is going to be your release. Liquid to gas is going to be absorbing energy. Okay? Well, if vaporization is liquid and gas phases, what does fusion have to be? Fusion is going to be solid to liquid or liquid to solid. So remember that. Liquid to solid, you are releasing heat, so it's going to be a negative value. And if you're absorbing, it's going to be a positive value. Okay? So notice how I said boiling / condensing, freezing and melting. You've got to know these terms. Okay? Think about water. Most of the time you're going to be asked about water, so just you guys know water. You deal with it on a day-to-day basis. Okay, but notice, you don't have to memorize these values. They are given for you on table B. You just can't be too lazy. You've got to look it up. You've got to have your reference packet out and look for it. But other than that, it's going to be pretty much the same as we did before. But notice how these problems change. This says calculate the amount of heat required to melt 55 grams of ice. So it says calculate heat. There's your Q. Okay, I'm looking for Q. And then I've got a mass, 55 grams. Notice they give me one temperature, guys. It says at the same temperature. So if temperature remains constant, okay, that's how you know it's a phase change. Temp is constant. It's going to be a phase change. You have to figure out what phase change it is. This is the key word you're going to be looking for. Things like melt or freeze or condensing or vaporizing or boiling. Those are your key words that are going to tell you, hey, am I using Q equals MC delta T, or hey, am I using Q equals MH something, whether it's HV or HF. In this case, melt means solid to liquid, so I'm going to be using HF. And notice 0 degrees Celsius, that's my melting point for water. So I look up HF, 334 joules per gram. Now let's just plug and chug. Q equals MHF. Q equals 55 grams multiplied by 334 joules over grams. Grams will cancel out, leaving us just joules. So when I do this math, all right, my answer should be 18,000 370 joules. Now ask yourself, is this going to be a positive value or is this going to be a negative value? Okay. Melting, I'm going from solid to liquid, so I'm absorbing energy. That means this will be a positive value. Okay, so I would leave it, and this would be my answer. All right, if I was going to round to correct sig figs, I would round to 2, so it would be this right here. It would just be, 18,000 joules. So pause the video, try this one on your own. All right, here we go. So I'm looking at how much heat is released. So Q, I've got a mass that is 455 grams. Condenses, that's my key word. Which H am I going to use? So it's HV. Okay, so I'm going to look at HV, that's 2260. Notice it's released as well. So what would be my final answer then? Okay, think about that. This is negative 2260 because we're releasing, we're condensing, we're going from a higher energy state, which is a gas, to a lower energy state, which is a liquid. Q equals MHV. So Q equals 455 grams multiplied by negative 2260 joules per gram. Grams cancel out. This is going to be a very, very large number. Negative 102, or I'm sorry, even bigger than that, 102,8300 joules. Okay, and it's negative because we released it. That's 1,000,000 joules that were given up. So just as a side note, guys, last thing, negative means released. So you've got practice to do. Ask for help if you need it. The hardest part is going to be figuring out what formula you need. Write down your variables and look for those key words like condense, melt, freeze, or if there's a temperature change. Until next time, see you later.